I will wait for 2 more minutes. Raining day.听不进去了，比赛。还是啊，这样有边哦。结果那个比赛都没有哇，还破个洞，我背后人家死了。我搬，我搬，我没有进场。
哎，汉伟，你submit了吗？没有哈。OK，几时要submit？
这个会，
因为我不能一直等下去啊。对呀、太迟也不能了。对啊，太迟也不能。这个拜日太迟，我应该也不会说。
到这么近，但是只有大，我可以多重新来看啊。所以现在这些做好那个大那个早，所以一上网课，你打算在那边找一切了？对不？啊，你先找一些，你先找一些。
做做做咩？做一次。哦，不懂哎。你可以坐在自己上网课，其实。
哇，是哦，今天有断了哦。哎，有人去个演唱会吗？太远，太远，看的是你那边人的 IP 来源。哦，是，哎，有环绕音感。哇塞，我们主要是这样。现在看一下，然后一边那个是这样加点，
环绕音感。
400多块，你看北京打的，对。
OK OK。小浩，你昨天做的 project 交了吗？你不是讲你昨天在做 project 啊？嗯，你说我们的啊，你是说我们别人的今天要讲？在这边，你们在这个上还有本，看看有什么？不要写的，嗯，本，啊，都 I think let's start. Um, Maybe today not much writing, but we will quickly finish up the tether series part. So yesterday I promised one examples that is a power series. So a power series looks like this: power event with coefficient 1 can converge uniformly on every closed interval, okay, such that this R live in between 0 and 1, but it doesn't converge uniformly on the open interval -1 to 1. Okay, so yesterday I somehow tell you that this is the reason of the domain we consider here. One is closed, the other is open. Okay, so this is something has to do with this interval here, the special thing about this interval. Okay, so we can use lemma from yesterday to prove that it is converging uniformly at every closed subinterval. But let's see why it doesn't converge uniformly on the open interval here. Okay, so I mean, you can suppose it does, right? Suppose, on the contrary, that it does converge uniformly there. Okay, so what's the definition of converging uniformly here? What do you start with? For all epsilon, there exists n such that for all small n greater than n, and for all x in your domain. Okay, so this means uniform means what? Every x have the same bit n. Okay, every x has the same bit n, such that the partial sum, okay, minus what? Where should this function converge to? You know where this function converge to? Yes, correct. That's right. Good, very good. So this guy converge to 1 over 1 minus x. Okay, this is the limit function we had discussed yesterday. Because this is what? S to the power n. It's just the geometric series. Okay, so you need to make sure this one less than epsilon. But to make this less than epsilon, what does it mean? Can you calculate further? We know the n partial sum formula, right? What's the n partial sum formula here? 1 minus x to the n plus 1 over 1 minus x. So this is the high school formula. Minus this. What's this calculation here? I think it's quite easy. What do you get? Minus x to the n plus 1 over x less than epsilon. So you need to make this term less than epsilon. Okay. You need to make this term less than epsilon. So can you see anything here or not? Any ragu? What is ragu? 怀疑，没有疑点，有没有证据？有没有疑点？ragu. Where your s live? -1 to 1. If you put -1 to 1, take n very large, what happens? Very small. But here, if your x very close to 1, what happens? Very small. Very close to 1. If x close to 1, what's the difference with 1? Very small. But you are dividing by a very small thing. So make the whole term become large. So denominator trying to make this term large. Numerator trying to make this term small. So 谁赢到最后？看谁快，对不对？所以这个是 dependent 了咯，要 depend 咯 ，it depends 哦。看你 n 快还是看我 s 快靠近一 depend 咯 ，got dependent already。如果没有看谁快的话，就没有 dependent 咯。这要看谁快哦。OK 了 ，OK。So what do we say here? So if you look at a fixed n and you take your point, because we need to consider for all point, right, for one n. So if you take your point very close to 1, okay, from the negative, because we are considering point from -1 to 1, what this limit becomes? You know how to compute this limit here? So if very close to 1, then my x is already positive. Okay, do you know how to compute this limit here? Cannot lop it out, right? Because top is 1, bottom 0. 0 lop it down need what? Cannot reduce lop it down. Just infinity, Can we just do that? Can or not? Yeah, that one because the top is constant for that case, but this one is taking limit on both numerator and denominator. Correct or not? I think a little bit, but I come out with this. So I write it as x minus 1 times x to the n plus x to the n minus 1 plus ... plus 1 plus 1. Maybe you wonder how I come out with this formula. What do you think? How I come out with this formula? Yes, binomial as mentioned, but how I think about this, how I come out with this step here. I can, yeah, sure. But what's the idea? You need to start. Remember, when we talk about n case, you need to always start with the simple case. N equal to 1. Can you solve or not? N equals to 2. Can you solve or not? Okay. If you start with a simple case, let's say x over 1 minus x, how to solve it? You can plus 1 minus 1. Does it make sense or not? Let me write down. For example, when x over 1 minus x, what can you do? You can write x. Okay, write s minus 1 plus 1. Okay, so you can write like this. The point here is I want to cancel out the x with the 1 minus x. X squared, what can you do? Also can do, what can we do? Minus 1 plus 1. Okay, and then you can see the pattern. Okay, so this is the pattern we want. Okay, so first year, I'm very scared of linear algebra. Why? Because first year, I asked you look at general and they're scared already. Because they don't know how to start with this first. So they cannot deduce formula like this. So you need to be able to see this formula using n equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, solve in the same way. Same way meaning what? I got a formula. Okay or not? It's not I straight away see this and then see this. Oh, I'm genius. No. Okay, not genius. We are not all not genius. So we start from here. Can you settle this case or not? Huh? Can you settle this case or not? Settle using the same way. Or not? Okay. Yeah, question.
Then x become n.
X become n. 什么意思？
X goes to.
Oh, so you mean this one, huh? This one. Oh, hey. Oh, yeah. Okay, so stupid x. Thank you. Okay, so why is this good? Why this way of writing is good? Because we can reduce this to the limit of sum of polynomial plus a function that we know what is the limit when we take x to 1. And this is the one that Jet said just now, 1 over 1 minus 6. Okay, what happens here? These are just finitely many 1 after you take limit. But this one is infinity. So infinity minus a finite number is still infinity. Okay. Okay or not? So if this terms go to infinity, that means you cannot make it as small as you like. Okay, at certain n. Does it make sense? Make sense or not? You keep an n, you cannot make this term as small as you like because your n need to cover all the point inside -1 to 1. If I get very close to 1, then I cannot make it small like epsilon. Does it make sense? So this n actually need to depend on x1. So it's not uniform. Okay, you get the logic? Question? Please ask question. Please ask. Okay, yes. Loha. What do you mean? Because remember, go back here. What do we need to do? This n has to work for all x in between this region such that this inequality is true. Say again, if I fix an n, this inequality here have to be true for all the point inside here. Say again. If I fix an n, this inequality have to be true for all x inside here. Okay. Say again, last time, third time. 重要的事情要说3遍. For every n, okay, for every n, this inequality here have to true for all x. What did I show? For any n, this expression here can make as large as I want if I pick clever point inside this region. What is the clever point? As close as to 1. Okay, no. At some point, I will pass by this epsilon already if I get closer to 1. Okay? Question? Stop the order for what? Small n and x. Mean you fix x and then you can change your n. In that way, I think you won't get contradiction. Yeah, I think in that way you can't get contradiction because it's exactly what we discussed just now. If you fix x, this part become constant. This x also become constant. So when n get large, I can make as small as I want. But the problem is when I make my numerator as small as I want, I can vary my x at a fixed n here. Yeah, I think the main problem is this denominator here. It's not x, it's not n. It is true that if you fix an x, if you take bigger n, you will get smaller as you like. But the other way around is not true. Yeah. Does it make sense?
I mean, this is a convenience to get an infinity.
I think this is the only way you can break the convergence, uniform convergence. Okay, now. So the problem here is the n have to work for all xy. Yeah, but if I take my x getting closer to 1, this expression will explode. You cannot make it as small as you like. Okay or not? Or question? Does it make sense? Make sense or not? So this one go to infinity means what? So this term here is greater than every real number, in particular the epsilon. Okay. Yeah, because you make it go to infinity, right? Meaning it is greater than every real number, in particular the epsilon we started with. Any question? Or question? Feel free to ask. 不要不问啊。How do you? Yeah, the problem is how you justify. Which one is what? Because both of top is convergent function, bottom is convergent function. But did we define what is 1 divided by 0? We didn't do that. Only when they are finite, then we can get a finite number. If it is 1 over 0, then I don't think we have this kind of proof that it is infinity. Yeah, because it's very dangerous when you have a 1 over 0. Maybe it's not diverging to infinity. Maybe it's just not like different divergence. So I resorted to this case because n is fixed already. So here it's just a fixed number. Yeah. But this part is infinity. Okay. Question? If you are worried about this part converge, this one diverge, maybe you can prove that this whole thing is actually diverging to infinity. If you are worried, yeah, if you are pedantic. Because what we prove is only for divergence, but by convergence function, then you can do the limit together. But if you are worried about, I think you can check this properly. But I think it's clearer from this expression here than straight away compute here. Okay, this is my point. Does it make sense? Okay. 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 In that case, so I think we can quickly finish up what we wanted to do. So next up is about this term by term differentiation and term by term integration. Okay, so what is term by term differentiation and term by term integration? So this is about power series. So if you want to differentiate the power series, what can you do? You can actually bring the derivative into every term. Okay, and then we know how to divide polynomials. Okay, just multiply by the power and then power take away 1. And then you keep the coefficient. Okay, so this is very convenient. Okay. This is non-trivial. Why is it non-trivial? Why is it non-trivial? 不简单。为什么 Why? Because this sum is infinite. 什么叫做无限的求导 Remember how we write down the sum plus dot dot dot. How to differentiate dot dot dot? Huh? How to differentiate the 3 dot? Correct or not? Huh? How to differentiate dot dot dot? So many things behind. But this one tells you that you can just differentiate every term if you know how to describe the dot dot dot. Does it make sense? But this one only work for power series, like this kind of form for now. Okay, power series. If you put Fn here, do you think it's differentiable? General Fn? Yeah. If you have a sum of general Fn, is it differentiable? Maybe no. Maybe, yeah. So we can try and check it. Okay, we will prove this inside the tutorial. And also, we have a counterpart for integration. Okay, so if you want to integrate, how to integrate the dot dot dot. Okay, we also can integrate term by term. Okay, so let's look at a flavor of how to prove this. Right. So let's say let's say from where? Maybe we prove from here. Let's say we know how to integrate term by term. Okay, we want to prove that this is equivalent to integrate the whole sum here. Okay, so how do we go through this process here? So if you sum these integral together, do an infinite sum, is doing what? It's taking the limit actually. Okay, limit of what? Of n partial sum. And then what do you do here? Because here is a partial sum, right? But your integral is linear. What do you mean by integral is linear? If you integrate fg is equals to integrating f plus integrating g. So you can bring the integration up, okay, from the finite sum. And then what's this partial sum here? This partial sum here converge uniformly. Okay, so actually you need to prove that this Sn converge uniformly at AB. Do we have this condition or not? So we know that this minus R to R is the interval of convergence for this power series. Okay, so we are looking at what is AB here. AB is just a subset inside this interval of convergence. So last time we say what? If you converge at a point, then it will converge uniformly at a closed subinterval. So you can regard this AB living in the closed subinterval that this function converge uniformly. Okay, so where it converge uniformly? It converge to converge to where? Converge to the infinite sum. Okay, converge to infinite sum. So last time what did we prove? Uniform convergence will preserve integrability. What does it mean? By uniform convergence preserve integrability. What does the preserve mean? Sequence of integrable function uniformly converge to a integrable function. Okay, so let me show you again. So where is it? So let me bookmark this. Let me show you. Need to remember this fact. Hello, 小童呢？你淋雨来？哦， Hey, I think last time we proved here. Uniform convergence preserve integrability. So what it says, if Fn converges uniformly to F, if Fn are integrable, then F is also integrable. Moreover, we know how to compute the integral of the limit. How do we compute? We just take the limit of the integral of Fn. So this is what? Limit of the integral of Fn is equals to the integral of limit of Fn. Okay, so the limit can and the integral sign swap. And you learn in abstract algebra, right? Commute. Okay, the commute. When can you commute? When your Fn converge uniformly. Okay, when Fn converge uniformly, then limit and integral sign can commute. You know, uniform only have uniform can. Okay. Okay. So just now we have this converging uniform property. So we also can commute. Okay, we can commute. But after you will commute, what is it? What is the limit of Sn? Is the infinite sum. Yeah, is the infinite sum. Does it make sense? Okay. Any question here? So the derivative one is a bit unusual, a bit. The proof is a bit long. Why? Because last time we know that even uniform continuity doesn't preserve differentiability. You need extra property. What is the extra property? You want the Fn prime. For the derivative of Fn prime, you also need to converge uniformly. You need to have extra property. Okay, otherwise you don't have. Okay or not? Does it make sense? Okay, so we will deal with it in the tutorial. Okay, so what we have discussed yesterday, I talked telling you that our power series always contain a point 0 as a point of convergence. So we can actually change this center. Okay, I can change the center. So I can define a power series that center as C, any C, okay, to be this form here. Okay, any C. So in our case yesterday, it was C equals to 0. Okay, so we can move around this power series here with this x minus c here, shift. Again, a shift line. Okay, so if I make this definition, we can have similar theorem before. Okay, for example, this theorem here. Then the set of power series of x minus c, okay, change it to x minus c here, will converge at the point C or what? Or on whole real line or the interval plus C. Okay, so you shift it to C. Okay, the interval of convergence. Does it make sense? Okay, because if you substitute zero to into this polynomial, this power series here, it no longer must converge. Correct or not? If you put zero, here, okay, maybe diverge, depend on x. But if you put c here, what do you get? You get the constant term. Okay, so it converge at c. So that's why we call it power series center at c. Okay. It is the place it always converge. Okay, no? Yeah. Actually, these are what we learned in calculus too. We just restate it in a rigorous way. It's the same thing. Okay, so we are trying to explain why it works. Okay or not? Okay, it's not something very new, super new. It's what you have seen before, just that we try to explain how it came from. Does it make sense? Okay or not? What time is it? 9:40. Okay. Yeah. Any questions so far? Okay, maybe we give a definition of Taylor series and Maclaurin series, and then we will take a break there. So next, we will study a class of a polynomial with a specific coefficient here. Okay, with a specific coefficient, which is the Taylor series. Okay. So if you have a real value function, okay, and you can find your derivative, then what can you do? You can form this power series here. What is this power series? This power series center at where? Like, this power series center at where? C. Okay, good, because this is x minus c. But I control the coefficient here. What's this coefficient here? It's the n derivative of f evaluated at c divided by n factorial. Okay. So if c equals to 0, if it is centered at 0, it is called a Maclaurin series. Okay. 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 So for example, let's give this example here. So what's the Taylor series of 1 over 1 minus x? What's the Taylor series of e to the power x? So what do you do? First, what do you compute? Fn. Okay, compute Fn. Okay, but now this one centered at 0. So you need to evaluate Fn at 0 and then divided by n factorial. Okay, so this is the answer. Okay, if you do it. I think the easiest calculation is this one. Okay, maybe you can check this. Is it true or not? Is this Taylor series Sn over n factorial? Okay, so every time you differentiate ex is what? Ex. Okay. But how you do this differentiation? This is what we did in tutorial 8. Okay, we define it to be a derivative of x. So ex evaluated at 0 is what? 1. So Fn0 equals to 1 for all n. Okay. Then what you left with is divided by n factorial time x minus c to the power n. But c here is 0. Okay, so this is the Taylor series. So you can do the same for 1 over 1 minus x. So you see, this Taylor series don't have n factorial. So meaning what? Meaning what? Meaning what? No. Oh, sorry. I was trying to ask why does the n factorial disappear? Why the divided by n factorial disappear for 1 over 1 minus x? Yes, so it means what? The n derivative of this 1 over 1 minus x will produce n factorial so that you can cancel with the denominator. Okay, so you go back and compute. Is it f? Is it 1 over 1 minus x differentiate n times evaluated at 0 is n factorial? Okay, if it's n factorial, then it will cancel with n factorial. Okay, now. So this suggests that, so this one would suggest that actually, if you compute, if you compute 1 over 1 minus x to the n times evaluated at 0, you will get actually n factorial. Okay, try and compute, check this is true or not. Okay. Question? Okay. So the rest of the next lecture, our goal is to show that f is equals to its Taylor expansion. I want to put a equal sign here. Okay. So when this equal sign will work. Okay, so this is our next, for the rest of the next hour. Okay, we will explain this. Why are they equal? If not equal, then 做来做么？对不对？没有这样无聊嘛，对不对？ But last time I remember how we motivate. Do you still remember how we motivate this Taylor series? What is the special thing about that prime? Not prime, yeah, prime. The n derivative. What is the special thing about it? Do you still remember how we motivated? So maybe give you some motivation first. How we motivate? Let's say we look at this one. Square, sorry, plus x squared over 2 x cubed. How we motivate this? So we also look at the partial sum. Okay, we look at the partial sum. How does EX looks like? It is. Okay, intersect at 1. Okay, so we look at the partial sum. Look at T1, T2, T3, like that, partial sum. Does it make sense? Okay, so what is the function y equals to 1? It is a constant line. Okay, so this is T1. T2, 1 plus x. How does x looks like? Y equals to x looks like this. Okay, but 1 plus x, what does it mean? Move up. Okay. Okay, I think this one a bit ugly. Let me draw again. How about 1 plus x squared over 2? I think we somehow saw this thing once. What's the root of x squared plus x plus 1? What's this? What's the root? Can you find this root? Quadratic formula. What's the quadratic formula? No root. No real root. Let me see. No real root. No real root. Okay. No real root. But wait, this guy no real root. Yeah, I think no real root. Okay, no real root. That's fine. But we can rewrite this, right? How can we rewrite it? X times x minus x plus 1 plus 1. Okay. So how can we draw this? Can I play a cheat or not? So what I want to claim is it should look something like this. Okay. And then what is T4? You have a S cube term. Okay, how does a S cube look like? Something like this. Okay, so you can draw. How can you draw? You could draw something like maybe this. Yeah, I think you can use GeoGebra. I can go back try and use GeoGebra, put these partial term together. But what can you see here? Can you see something in common here? They all intersect at 1. Okay. And then if I draw it more precise, you can see that the interval that they intersect will grow. The interval that intersect will grow. So what do I mean by here? So if you imagine T1 intersect at EX, there's only one point intersect. But if you pick T2 intersect EX, it will intersect around a small region. It's a tangent, not quite tangent, but it's a line that touching EX more. And then T3 in theory should touching even more. Okay, this part intersection here should touching more. And then for T4, it will touch even more. Okay, so you can imagine that when I add T5, T6, T7, T8, it approximate my EX better, and better. So that's why we say that this power series here converge at every X. Because if you get larger and larger T, this curve here will resemble your EX better, and better. That makes sense? Okay, now. Yeah. So what do we do at the coefficient there? So we are study the rate of change at this point. Okay. 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 Later you will see how we approximate, how we show this. How do we show this inequality? Equality. Okay. Any question? Before I take a break. Yeah, let's take a break until 10. Okay. Yeah. Excellent. Okay. And I absolutely over.
什么叫什么叫就是训练到不行
有啊，
啊，然后它是 F 的那个整个心理学是
再讲一次
那个上
，x 要等于那个等级啊。等一下我们要做，现在还没有，现在我们只是算 L C 的算出来。等一下我们要 show 它的钱，在什么情况下？
基本 X 里的
微分乘上方形就是一方面，对不对？的猫头边，对，这真的很奇怪，确实是很奇怪，所以我们要证明后，真的是很奇怪，所以我们才要证明。对对对对，等一下我们要解释为什么这两个问题不一样。现在他们两个是啊，你等我读了，我再回复你啊，我还没有读。
点滴到你多少钱？3块钱。
昨天有人干那个新装的那个零食机，但是他没有开办，然后设置是1毛钱，然后有些人就拼命买，买到那个保安过来就分了。
最近很喜欢有几个人是，我就是啥。 反正是吧。
感谢。这个是。
不要测。Hello, testing. OK，最后1小时啊，黄金最后1小时。OK， right. So you are right. Just now, Jack asked a question during the rest time. Y equal doesn't look the same. One is 1 over 1 minus x, but the other side is sum of monomial. Okay, why they have to be equal? Okay, no point, right? There's no point why they have to be equal. So the definition also didn't say that they have to be equal. No equal sign for now. Later, again, by the end of this hour, we will prove that why they are equal. Okay. Now, no, not equal. So one thing I want you to note is they have the same derivative. At every level, they have the same derivative. How should I prove to you? How should I prove to you? How should I prove to you? Okay, let's prove to you. Let's say, what is e to the x differentiate once? Let's start a new page. Okay, maybe start here. So e to the x differentiate once at 0. Okay, we only discuss derivative at 0. At the point you differentiate. Sorry. At the point where your part the Taylor series centered. Okay, so our center is 0. So we know that this is always 1. But how about the Taylor expansion? How about Taylor expansion? How you expand this incredible thing? How do you differentiate this? Huh? How to differentiate this whole thing? Yeah, term by term differentiation 学了要用的 ，OK 要用。So we can differentiate term by term. So we can bring the derivative into every term. So who survive? Survive here. Everyone but one. Okay, very good. That one is before substitution, at x equals 0. Okay, so that one is before substitution. So what do we left with? 1 plus 2x over 2 factorial, right? Plus 3x squared over 3 factorial plus dot, 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 dot. But remember, we only calculate this derivative at the center. Center is where? X equal to 0. So what do you get? 1. They are the same. You can do it for second derivative. Okay, so imagine if you do second derivative here. Okay, here is easier, it's the same because always for e to the x, you always get ex. But here is different, Who survive if you differentiate second time? survive. Only the s squared term here survive. Okay, this term becomes what? 3 times 2. Okay, but we evaluate at 0 again. So disappear. What do we left with? 1. So can you see the pattern or not? If I going to differentiate 3 times, what happens? The third time is this coefficient will stay. So can you see what the n factorial is doing or not? It is cancelling with the derivative of x to the n. Okay, okay or not? So later we show equality based on this equality on the n derivative evaluate at the center. Okay, later we'll use this fact to prove it. Okay, can you see from this example here? Every derivative is the same. These two sides. Okay, okay, good. Okay, so later we will use this fact to prove it. Okay, good. So I think you need to record this calculation here. Okay, what we did in calculus 2. Okay, this Taylor polynomial. Okay, what kind of question we had last time? Approximate the function by a Taylor polynomial of degree 2. Okay, so we compute what is T2, and then we check what's this accuracy of this approximation. What do? We use Taylor inequality. So later you will see we will prove these this machinery here. Okay, please record this thing, and then now we will do it rigorously. Okay, so first thing first, if you want to show infinite sum converge, what do you need to do? You need to deal with the partial sum. Okay, so let's give our name a partial sum. Our partial sum is called the n-Taylor polynomial. Okay, if the Taylor series truncated stop at certain n, we call it a n-Taylor polynomial. Okay, Taylor series is what? You can keep going. Okay, so if you stop at some n, we call this Taylor polynomial. It's a polynomial. Okay, and then we call it n-Taylor polynomial so that you know where to stop. The claim is if your function is n differentiable, then there exists a unique polynomial Pn. Okay, so this n polynomial is unique. Okay? This n polynomial is unique. Okay, so how to prove this kind of statement? What do we need to show? Two things we need to show: existence and uniqueness. Okay, existence and uniqueness. Okay. So how to show existence? I think existence is easy, right? You just need to compute the n derivative. But n derivative is already given. You can compute it. Okay. So maybe the part that's non-trivial here is why unique. Why I can't make other combination? Okay, why is it unique? Okay. So let's see, why is it unique? Let's say I have the other power series that looks like that. Okay, that looks like this. C0 plus C1 times x minus x0 and so on. Okay. Then what do? I want to show that it is the same as the Taylor polynomial. Okay, so how do I show that they are the same? So what's the property that defines Taylor's polynomial? Let's go back here. So the property is here. How do we define Taylor polynomial? It has the same n derivative as f. Okay, so this is the thing that defines this n Taylor polynomial here. So we want to define a polynomial that has the same n derivative with f. Okay, so The only way, so the claim here is the only way to put coefficient for your power series is just putting the n derivative divided by n factorial. Okay, so this is the claim. So what is the Taylor polynomial definition? You want the power series that has the same n derivative as f. Okay, okay or not? So how to show uniqueness here? So let's say you have another, okay, another power series that has the same derivative as f. But what do you get here? What do you get here? If you differentiate this guy, k time, what is the value you get? It's actually k factorial over ck. Not this derivative have to evaluate at the center. Okay, after you evaluate at the center, what left is k factorial over ck. So remember how we get this k factorial just now from the calculation. We are dividing the power of x. Okay, here not. So this term here have to be the same by definition as the k derivative of your function. Okay, so you need to make these two the same. So if you make these two the same, meaning ck can only be the n derivative divided by k factorial. Okay, no? So this is how we deduce the Taylor polynomial. Okay, or how we define the Taylor series. Okay, maybe you think that, oh, Taylor series come before this. Actually, it's not. Actually, we want the Taylor polynomial first. Okay, we want to approximate. And then we see that, oh, if I define Taylor series in this way, then I get what I want. Okay. So this is how we started to define the coefficient of Taylor series using n derivative divided by n factorial. Okay or not? Does it make sense? Because what do we want? Definition of Taylor polynomial. We want a power series that has the same derivative at with f. It turns out very useful at this thing. Only derivative, very good. Okay or not? Okay, later we'll see why they are equal. Okay? Does it make sense for now? Okay or not? So this is the unique one. No, no other polynomials that have the same n derivative with f. Okay, if they don't look like this. Okay, they must look the same. Does it make sense? Okay, okay, so this is about n polynomial. Next thing is this one is a hard thing that I ask you to do in your assignment, right? So if you know that your function is n plus 1 differentiable, and then for the previous fk, it is 0 when you evaluate it at s naught, then your your fx, all your points can be written in terms of n plus 1 derivative. But this is a point, but this is a function, right? So this function work for where? Work for every x not equals to the center. Okay, not equal to the center. And just this polynomial, this monomial here, multiplied by the n plus 1 derivative evaluated at, what is this c? This c here is something in between x and x naught over this n plus 1 factorial. Remember how we proved this? You remember the assignment, the big F small g and big G, big F big G? Yeah, so this is proven by the Cauchy mean value theorem here. Okay, so I mean, we can rewrite this, right? Let's rewrite this. So maybe this form is not good for you. How about this form here? Okay. Maybe this form is not good again, huh? So maybe let's put this form again. Can see or not? Very hard to see. Okay, let me change some color. Better. Okay. Does this remind you to use a Cauchy mean value theorem or not? Not quite. Not quite. Or how? I think we need to go back more step, right? To see the Cauchy thingy. What's the Cauchy mean value theorem? So let me move here first. So let's bring the statement out. What's the Cauchy mean value theorem? Fy minus fx over plus x equals to f prime c, is it? There's this a c in between y and x. This one Cauchy or not? Not this one, huh? F prime c over g prime c. So you mean the other function, is it? Like this, huh? G c dy minus gx over f prime c over g prime c. Okay, thank you. C over g prime c. Okay, thank you. Okay. Okay, good. Okay, so what's the relation between here and here? Any relation? Shall we solve it here? Huh? Solve it here. Let me see. Okay, I think we should send out this assignment question. So what's this assignment question? So what's the assignment? We did the mean value theorem. Oh, 3? 3 or 4? Yeah, 4. Yeah, inductively applied. So I was wondering here. It is this part here. Yeah. But in this case here, we have some extra thing here. Let me think. Do we want this extra thing here? Okay, this one is a bit different. This is a bit different. Let me check out tutorial question 1. Okay, where's tutorial question 1? Okay, let me check. We don't want to stop here. Let me come up with this tutorial question. Okay, here. So what do we do here? Okay, so what we had is this f. Okay, f is there's a typo here. This g, this z here. So we regard the denominator as the g. Okay, and then we regard the numerator as what? As this part here. Okay, this fx minus fx naught here. What can we do here? Huh? At the first level, we can use I think something wrong here, right? This should just be a g, f prime and g prime. Okay, and then we apply again. Okay, we apply again. to f prime x1 over g prime x1. Because what do we know? We know that f to the any power of differentiation derivative of s naught is 0. So I can simply add f prime x naught here. But g prime x naught, this is based on the nature we define g. When you evaluate at x naught, this is also 0. So we are adding 0 here. But the good thing about this expression is I can use Cauchy mean value theorem to find another point in between x1 and s0. Okay, obviously this x2 is in between x and x0 because x1 is already found in between x and s0. Does it make sense? x1 是在 x0 跟 x 的中间。如果你找到 x2 在 x1 跟 s0 的中间 ，s2 是不是在 x 跟 s0 的中间？是哦。Okay, so you can keep finding this x2, x3, xn, or keep finding this xn until you found the n term, n plus 1 term. Yeah, n plus 1. N plus 1 guy. So this n plus 1 guy is still living in the s0 and x. Does it make sense? Okay, ma? My question is n derivative only. Yeah, my question is n. Here is up to n minus 1. So this is differ by 1. Does it make sense? So mine up to n plus. So the one in the lecture not up to n plus 1, no? Here only up to n, no? Because it is only differentiable up to n minus 1. Okay, yeah. Okay. Does it make sense? Okay or not? So what do we do actually is where is it? Okay, so what we do is we set who is as who. We set f to be f, and then g gx to be x over x naught. Okay, does it make sense? Okay or not? Yeah. So here, what do we do? So let's put y as x, and then put x to be s naught. So then we will get something familiar here. So we'll get fx here, and then gx here, x naught here, and gx naught here. Okay, but what is gs naught? Gs naught is always 0. Okay, but what is fx naught here? Also 0. Okay, so you can do this, and then you can keep apply the Cauchy mean value theorem to f prime c over g prime c, and then add 0 to them. Okay, add the 0 to them. Does it make sense? And then what do you get? You add f prime prime, maybe d, and then g prime prime d. But where does d live? Does d live in between c and s naught? But if you live in between c and c naught, it also implies that you live in between x and x naught. Okay, so you are trying to reducing the interval. Does it make sense? Any question or not? Okay. Question? Your question? Yeah. Yes. Y has the n plus 1 factorial. N plus 1. You mean this n plus 1 factorial here? Let me think, why is there n plus 1 factorial here? So in this case, should we define my gx to be? So in this case, let me think. In this case, I think, should we define my gx to be like this? Plus 1 factorial. We can do this, right? Let me think. It should make sense, right? Let me think, where does n factorial come from? Okay, so I think it's not this, but it's coming from this term here. Okay, so let's rewrite here. So what do we have here? So let's write all together what we have. So what is fx over gx? Is equals to fx. So let's write down the chain. So to be precise, let's put 1 here, x1, so that we can know what is the chain doing. Okay, can everyone see what is going on here? So here I add a 0, add 2 zeros, and then I use Cauchy mean value theorem, and then I add 2 0 again, and then I use Cauchy mean value theorem. Okay, and then I keep doing it. S0, Cauchy mean, S0, Cauchy mean, S0, Cauchy mean, but I stop at the last place I can differentiate, right? I stop at f prime prime, no, okay, n plus 1 time of s n plus 1 over g m plus 1, g m plus 1 of next one. Next. Is it Sm plus 1? Yeah. Okay. So what is this n here? Did I copy the wrong n? I feel like I copied the wrong n here. Can someone check this n? This is in the, let me check. I feel like I copied the wrong n. This book here. I copied the wrong n. Where's the Taylor part? Chapter 8. Can anyone go to chapter 8? What is this? I found this statement here. N plus 1, huh? Otherwise, it won't survive. It won't survive until if you take the derivative, it won't survive. Okay, good. Thank you. So it should be n plus 1 here. Okay, so what's this n plus 1 here? So you want to differentiate this guy up to n plus 1. This guy. N plus 1 time. What do you get? What constant? Huh? N plus 1 factorial. Regardless where you evaluate, because it is a constant function. So this is the n plus 1 factorial. So where's this part coming from? This is coming from all the way from gx. Okay, no. So this implies that fx equals to fn plus 1 over gx. So gx. Okay or not? Does it make sense? Or question? Question or not? Any question? So gx is here. Yeah. Okay. Or question? Question? Feel free to ask. Mm. 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 What range? Ho Chi Minh value. So what's wrong with that? You can take what other point. The point have to be strictly in between x and x naught. That exists. I don't know where is it that exists. But it must be in between x and x naught. Jump what? Don't get what you mean. I don't get what you mean. What do you mean by jump? Jump where? Why are you jumping? Uh-huh. Then why are you doing that? You mean how to pick this Sn plus 1 or what? How to pick this? What is the range you can take? So throughout this proof, right? Meaning what? This Sn plus 1 is quite close. Okay. Let me think. Okay. In that case, I draw this picture then. So it actually depends where is your x and where is your s naught. Okay. And then the first thing you will pick is x1. The second thing you can pick is x2, s3. So the Sn plus 1 is by theoretically is closer to s naught than x. Because every time how you pick the Sn plus 1, you are picking between x naught and xn. So theoretically, this Sn plus 1 is closer to s naught compared to the first x1 you pick. Okay, no? Okay, so Sn plus 1 is living here, for example. Does it make sense? What do you mean by squeeze? Squeeze here? How? You mean move this guy here? Yes, but relative to x1 is still closer to x0. But you cannot make, the problem here is you cannot move this si. This si is given by Cauchy mean value theorem. It tells you where is. Okay. Maybe there's a choice is very close to x, but there might be choice also closer to s0. Exists that exists. Okay, is that exists. Okay, no. You cannot make it is that exists. No. Yeah. 他给你的，你不能够跟人家要求什么，好不好？人家给的就不要要求这样多了。OK 吗？This is the exists. Okay. Okay, now maybe it's closer to x, but maybe there's another choice it's closer to s also. Okay, so if you pick this choice, maybe you can pick some other Sn plus 1 here, but if you pick this choice, Sn plus 1 would be even closer. Okay. So this exist is quite strong. So wherever you exist, then it will find another one. Because you can exist again, and exist again. Okay, now between 2 points. Okay. Okay, good. So how to apply? So in this case here, if I can write my fx using this n polynomial here, I can take the difference ex minus this whole bunch of things. So they have the same first derivative, right? This is the definition of Taylor series. So their difference, the n derivative will be 0. because they cancel out. So I can write it as I can write EX minus this n Taylor polynomial to be equals to this term here. What's this term here? This is the n plus 1 derivative factorial, n plus 1 derivative over n plus 1 factorial times x to the n plus 1. So I can write a exact form for EX, okay, using this. So for every truncation, I can do this. Okay. Yeah. How nice is this? How nice is this? So how nice is this is I make something not polynomial into a polynomial function. Okay. With this coefficient here in the last term. So what's this last coefficient here? This is the n plus 1 derivative evaluated at C. What's C here? There exists a C. Good. So there exists a C between where? Between 0 and x. So this one, this C here actually depend on x. You can change one. Depend on x. For every x that exists a C. Okay, so this C here actually is depending on x, to be precise. Okay, so this C is a function of x. Okay, no? So in principle, this one is constant is almost not true 如果这边是 constant 怎么可能一个不 polynomial 的东西写成 polynomial？ 这样的意思是这个是 polynomial 其实但是它又不是所以 actually you need to control with the other function here. So there are two functions, product of two functions here, actually here, because this C is depend on x for every x there is OK， 所以这里其实是一个 product of function， 其实 EX 又出现在最后一个 term 里面，会很什么？我只是把 EX 换成另外一种写法罢了，我让它写成一半的 polynomial， 但是哎呀还是解决不了，再把 EX 换回来。但是这边有一个神奇的地方，但是这个 E 不是在 evaluate x 但是这个 E 是在 evaluate 一个卡在 x 跟0中间的一个点。Does it make sense？ 好，yeah， 你可能觉得不是很好啦，但是 yeah questions， 确实，就是你把这整串东西再塞进来这边，是不是你的意思确实可以啊，没问题啊 ，no problem 啊，没问题呀，可以，你可以把整串类似的东西再塞进来这边，所以是整串加上整串就一个 EDX maybe EEX， 然后又 EFX EGX E 什么 X。可以，inductively 可以。等你那个 CGDEF 越来越小，越来越靠近水，越靠近yes， 越来越靠近。OK， 耶，没有错。但是越来越靠近零代表什么？这个东西越来越靠近1。可以的，可以 ，no problem。But at the expense of what？ 又加了一整串东西进来了，又加了一整串东西塞在这边。大家知道我们在讨论什么吗？知道吗？我们把同一个这么大的东西塞在这边上面，但是这个 CS 要变了它要变成一个 CS 跟0里面的一个点，然后我们可以一直这样重复。但是跟原本的什么差别呢？我又多了一整串的这个东西在这个前面。你身边小 on this guy， yeah， 可以 ，no problem。Okay, yeah. Okay, and then what's good about this? This is the main thing, Lagrange remainder theorem. So what does this say? That it says that fx 就是刚才那个 example，fx can be written as n Taylor polynomial plus this remainder. We call this remainder. Okay, we call this remainder here. Actually, that term is the Taylor remainder. Okay, remainder of the Taylor function. Yeah, and then we can prove that. What do we prove here? Yeah, we prove that this is the remainder. Okay, exactly this this lemma here. Okay, this guy is the remainder. Okay, because why? Because 我们就是要制造这个条件 the derivative is 0 at every level. But Taylor polynomial, why do we create it? We create it such that its n derivative is the same as f. So when you take the difference between n polynomial and f, the first n derivative should be 0. Okay, so what you left is this remainder here. Okay, does it make sense? 懂什么意思吗？不懂？哎，讲太快了，跟不上。OK， 听好来呀，再听一次。How to use this lemma? N derivative have to be 0. First n derivative has to be 0. And then fx will be equals to the last derivative in terms of last derivative. So you got a function. You got the n Taylor's polynomial. What does n Taylor's polynomial do? The first n derivative is the same as f. So if you take f minus n Taylor's polynomial, what's the derivative here? What's the derivative? 0. So you can apply this lemma here. So the difference between these two functions, what's the answer? Fx equals to the m plus 1, fn plus 1 derivative. Okay. Does it make sense? F minus p and f equals to the same. Does it make sense? 听得懂吗？啊 ，p and f 是什么 ？n Taylor polynomial，n Taylor polynomial 来干嘛？它的 n derivative 是和 f 一样，把它们两个相减 ，differentiate 一下，是不是它的 derivative 都是0前2个，对不对 ？Then 我们就 apply 这个 lemma to f minus p and f equals to f to the n plus 1. And then this thing is what we call the Taylor's remainder. Okay, does it make sense? 就是 f 减掉它自己的 n Taylor polynomial 剩下来的东西，就是这个 Taylor's remainder fn plus 1 c over n plus 1 factorial time x minus x naught to the n plus 1. Does it make sense? 合理吗？可以吗？ So this is a corollary here. Okay, so this Lagrange remainder is a corollary because if you take f minus this Taylor polynomial, what is left is the remainder, Taylor remainder. OK 吗？我们怎样 prove 到这个？还记得吗？加2例0，扣7一下，加2例0，扣7一下，加2例0，扣7一下。OK 吗 ？OK。Cauchy mean value theorem apply to 谁 ？f 和这个特别的 function。Okay, 把这个特别 function 就是拿来我们 build 我们的 power series。OK 了 ？OK 啊，可以感觉到那个theory 吗 ？So if your function is just a polynomial of degree at most n, then corollary is the n Taylor polynomial for p is just p itself. OK， 说什么意思？如果你有一个 degree p 的 polynomial， 你去找它的 Taylor n Taylor polynomial， 它们是一样的。怎样 prove？ 怎样 prove？ 就拿 px 减 pnx 就好了，得到什么 ？p 的 n plus 1 derivative over n plus 1 factorial 乘这个东西 ，but 我的 degree 只有 n 哦。什么是 n plus 1 derivative of degree n 的东西？比如说你有一个 Sn， 你有一个 S2， 但是我要 differentiate 到3，拿到什么0哦。So this term is 0. So proving what? Px equals to Pn f. But f here is P lah. Okay. So this is for a specific f. This f is polynomial of degree at most n. 特别的 f. Okay. Okay 吗？ Does it make sense? Okay. So in general, what to do? Okay, in general is we have to start with a function that is infinitely differentiable first. Okay, in general. Then f is equal to this infinite sum of n Taylor polynomial. Okay, if and only if the remainder go to 0. Okay, the remainder go to 0. How to prove this? Okay, so if you can write your f as this infinite sum, it means what? F is equal to the limit of this partial sum here. And then what do you do? You can move this limit to the other side. Okay, and then you can bring the limit up because fx doesn't depend on n. Okay, and then what do? What is fx minus this Taylor polynomial? Is the remainder. So you need to make sure that this remainder go to 0. Okay, if and only if. Does it make sense? Okay, so I mean, we can give you an example here. Let's look at our running example 1 over 1 minus x. Okay, so 1 over 1 minus x geometry series, right? So the n polynomial is what? The partial sum of power of x. Okay, so I want to prove that this Rnx is converging to 0. So what is Rnx here? Fn plus 1 c over n plus 1 factorial times x to the n plus 1. So how to bound this guy? So I've computed is this x to the n plus 1 over 1 minus c to the n plus 2. How to bound this guy? So where is this c live? This c live between 0 and x. Okay. So there are two cases this c will happen. This c is either less than x or greater than minus x. But you need to consider this x to be negative also. Okay, so that's why I put an absolute value here. So how to bound this c? Actually, this c can be bound by absolute value of x. Okay, I mean, okay, let me write down this in a better way. So this implies that c is less than absolute value of x is greater than minus absolute x. Okay. Okay, this will implies what? This will implies that minus c is greater than minus absolute value of x. This implies what? 1 over 1 minus c is less than 1 over 1 minus absolute x. Okay, so this is how I found it. But what is this term here? If you write into this term, cancelling here, what do you get? Do you get 0 or not? As n go to infinity. You get 0? Yes. Let's think about it. So this part is constant. This x is also a constant in between minus 1 and 1. So it's what? It's 1 over absolute x. Greater than 1. Sure? Greater than 1. Yes, yes, yes. Then minus 1, you get something small. Sounds weird. Huh? Bigger than 1. Why? So here what happened? In between minus 1 and 1. So 1 over that thing is what? Greater than 1. Okay. And then something greater than 1 minus 1. Take a number and think about it. 0.2, for example. 1 over 0.2 is what? 5 minus 4, 5 minus 1 is 4. 4 get very large is infinity. Then this one go to 0. 0.2 is correct. Anything will go wrong or not? Let's get something very close to 1. 0.8. Huh? Including 0 or not? Yeah, sure. Does it include 0? Should we include 0? Let me think. Why? So this x, where should we consider this x here? Well, let's come back to this statement here. Pointwise. Yeah, what happened at x equals 0? Oh, yeah.
And I guess like the very first equality,
Mhm.
0 power n plus 1 is just 0 and the whole.
Yeah, so I think we need to separate this calculation. So let's separate this calculation. At s equals 0, fx 0 is equals to 1, which is equals to p what? p and f for all n. Okay or not? So at that point, we calculate it straight away. Okay, but for the other point, what should we do? Should we claim something? Should we claim that 1 over 1 over x is strictly greater than 2? Strictly greater than 2? Can we write like this? It's not true, right? This is if and only if 1 over 2 is greater than x. Okay, this is not true. Yeah, so how do we prove this one? If it is greater than 2, greater than 2 also not enough. Greater than 3, maybe it's enough. But this one have to be true for all less than number 3. Not very good. Okay, let's try and think about this, check this properly. Okay. Yeah. Any idea? Any idea? Any idea? Any idea? If I put 0.8, what happened? The problem is when we get very close to 1, is it? So let's say what number is very close to 1? 0.9. 0.9, what do you get? 10 over 9 if you differentiate. Yeah, I mean fraction is better, right? 9 over 10, 10 over 9, then you get 1 over 9, 1 over 9 to the n plus 1 time. 9 to the n plus 1 times 1. 1 over n plus 1, right? But we need to invert it again. It becomes very big. Crazy one. Okay, I think we need to check this. Okay, let's check this properly. Because because remember that we learned that 1 over 1 minus x should be equal to this infinite sum for the point inside here. So I think we should be able to check this. Okay, maybe this bound is not good. I think we need to think about the bound again. Yeah, no. Okay. I think we need to check this again. Okay. Actually, this is quite hard to check for this ENX. But if you have this property, then it's good. Okay, if you can have this, you see, a bit similar to this Weierstrass M test here. But what you are bounding by M here, this is N derivative. Okay, if you can do this, we also can prove this function is equals to the Taylor series. Okay, so if you can do this, we can equal to the Taylor series. So you can apply this in particular to the EX case. Okay, so this one is how to say, stronger condition here. Okay, but this ENX here, I think we need to check again for this guy. Maybe this bound is not very good. We have to check this bound again. Did I computed anything wrong or not? Yeah, I don't think so. So, but this bound seems like not good. Yeah. Yeah. Any question? Yeah. I think we need to rewrite this part, huh? Any question? If don't bound, what do you mean? If don't bound, the question is how to show this guy go to infinity, go to zero. Yes. Where are you talking about? This guy? Mm-hmm. What happened to this guy? Uh-huh. And what? How to make this guy small as you like? Okay. Never mind. Yeah, try and think how to make this part here small. This part here. How to make this thing small for every x. You can fix x first, and then see does this n make it disappear. Yeah, what? Minus c over absolute x. Let me think. What do you mean by that? Huh? Yeah. So the problem is here. I think is it possible? Not sure. Because you see, the problem here is they're running two power here, but I make it to run at one places. So if I want to make this small, meaning what? I need to make this one large. If I want to make this large, I need to make this bracket here large. If I want to make this bracket here large, I need to make this fraction large. If I want to make this fraction large, I want to make this fraction small. I think for value that is close to 1, we need to do different analysis. Otherwise, this analysis I think don't work. This analysis I think only work when this difference here is greater than 1, strictly greater than 1. If the difference here is strictly less than or equal to 1, I think we need to do different analysis for those points. Otherwise, it wouldn't work. I think this bound. I think we need to add extra analysis here. Like we add the extra analysis for 0 point. Okay, I think we need to. So let me write down here. We need to do, I think, suggestion. Do different analysis for points that is 1 over x minus 1 that is less than or equals to 1. So what are these points? These points are points that are greater or equals to 1 over 2. I think we need to do different analysis for this point. So what are these points? These points are x greater or equal to half or x is less than equal to minus half. But we restrict our point in between 1 and minus 1. I think we need to do different analysis on this point. Okay or not? I will fill this part into the lecture note. Okay, does it make sense? Otherwise, this bound I think don't work. Shouldn't be working. Yeah. If we cannot bound this, then you can prove that this inverse series doesn't work at -1 and 1 actually. So we should be able to do it. Otherwise we need to. Strictly between -1 and 1, so should be for all things between -1. Otherwise, if okay, the warning is here. Warning. If we cannot do it, then our equality here only will work for x in between half -half to half only. We shrink the convergence. Okay, so I think we should be able to do this. Okay, we have to do it. We have to do it. we will change the textbook or if it's not true. So it have to be true. Okay, let's do a different, because if you check point wise, it works, right? Correct or not? Geometry series, it works. Yeah, geometry series will work for point wise. So it's just our bound or problem here. Okay, so before we left, why no one coming to class? Okay, never mind. 最勤劳就是我们了。算到最后1分钟。Okay, before we leave, so some fun example is you can look at this non-analytic infinitely differentiable function, meaning what? You have analytic means to have a Maclaurin series representation. So non-analytic is you cannot write down the Taylor series expansion, but you can differentiate it. But you cannot write the Taylor series down. Okay. So the example here is in Fitzpatrick. So the only place that have this Maclaurin representation is only at a point only. The other point don't have. Okay, how to construct this? Quite interesting. So you use e to the -1 over x squared at every point other than x0. But x0 jump. I think this graph is something like this, if I'm not wrong. I think it is something like this. Then put a 0 here. Okay, if I'm not wrong. Should be symmetric because this is even. Okay. But I'm not sure it's whether like this or like this. Okay. Okay. It's supposed to connect, but you throw that point away. Yeah. Okay. And then the other example is you are continuous function, but not differentiable. No place you are differentiable. Okay, so you create a function and then you're going to prove that the limit of the secant function doesn't exist. Okay, so this is in the Petrovic. Fig factory also have, they do a longer construction. Okay. So to give you an idea how you do your project too, so this is what I did for your summary. Okay. So we have been like 15 weeks, we actually do quite a lot of things. If you can digest all of these, I think you can be the top 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, top 14 in the Malaysian. Top 14 Malaysian. Seriously. I don't think anyone can digest so many things in a 15 weeks. Okay, so you are top 15 in Malaysia if you can digest all of this. So where do we start? We start with English word, alphabet. Okay, and then we put it into words, and then we define logic, and then we use logic to do natural number, right? Like what Seng presented, natural number. Yeah. Hey, speaking about presentation, I haven't give you feedback. Actually, I feel very relieved and very happy after seeing your presentation because we did one in calculus 2, right? And then we did one again in MA1. So I can see your improvement. Okay. In calculus 2, you were like 卡一下但是 in MA1 比较顺畅了，比较自然了。OK， 而且不敢讲的也敢讲了。OK， 说非常好。非常好的 improvement， 就这个就是学生要做的事情，你就是要一直improve 你自己，好，就非常好，很好。OK， 你们的分都很高，其实，如果你们叫 project， 我会把那个分数写给你们。OK， and then natural number what we do, and then after natural number we do real numbers. Okay, after real numbers we can look at a bunch of real numbers. Okay, look at sequence, and then we look at functions between real numbers. And then this function we spend a lot of time because there are 3 main properties we need to consider here: continuity, differentiability, integrability. Okay, we need to do all these. And in between these, we have all sort of theorem, definition. I list up the main part here. And then integrability, okay, the book sum, the book integral, prima integral, okay. And then there's a part that we left sequence, okay, jungle of sequence and series. So this is another story already. Sequence of real number, series of sequences of real number, and then sequence of real value function, and then series of sequence of real value function. Okay, so you can compare, okay, compare what we use, what we did here. Okay, so in particular in the sequence of real value function, we export everything we learn for function into the sequence of function here. Okay, so we can ask about uniform continuity, continuity, differentiability, integrability. So 看到 function 就有3个东西你要想罢了 ，continuous 吗 ，differentiable 吗 ，integrable 吗，就这样。OK 了，就这样吧。看到一个function就问这3个问题吧。好 ，continuous 吗 ，differentiable 吗 ，integrable 吗 ，that's all， 就结束了，function 就这样吧。OK， 然后so the last part is the series of sequence of function, where we use the knowledge to power series, and then going even more specific, the Taylor series. OK 了 ，then 我们就停在 Taylor series 这整个course. Okay, I will finish up this Taylor series part. Okay, and then we will finish up the convergence just now. Okay, anything you want to ask? If you can't down, I will post this to the lecture notes. If you can't down, I got highlight. Why I highlight? So you want exam ticks, right? So this is the thing you need to know to be able to answer the question in the exam. Okay, the highlight topic. You need to know how to use them. You need to know what are them, how to use them. Okay. The highlight part. And also I will put out the definition and theorem sheets that I will provide in the exam so that you will roughly guess what is the thing that involved in the exam. Okay, then you prepare based on this. Okay, so I also understand that there's plenty of content inside here. So to reduce your revision work, so you follow these highlighter. Okay. So this is the thing you must know before you coming into exam. Okay. So in exam will test you how do you know how to put this thing together or not. Okay, does it make sense? Okay 吗？可以理解吗？ OK，所以我 highlight 的这些部分，你肯定要知道，肯定要知道它怎么用，它相关的题目怎么去用它，就够了。OK，没有考以外的东西。OK，没有 tricky 的东西。呀，没有 tricky 的东西，final 没有很 tricky，就是要考你怎样懂把这些东西用嘛，怎样会拼嘛。OK，tutorial 题目有相关的，你一定要会做。assignment 也是，你要会做的意思是说啊，你要怎么去用它，不要背答案罢了啊，不要背啊，背是没有用，背不了一时，背得了一时，背不了一世。OK 吗？这是我相信的。哎，我们需要拍个照吗？可以找人来拍一下吗？快快拍一下，找一个 guard 还是外面抓一个学生进来拍？台本有在没？找一个人来拍一下，石英还是金上可以帮忙一下吗？去外面找一个人进来拍一下，快快拍一下。